Okay, so hello everyone. I sent an announcement just a few minutes ago. So it's about our teaching plan for the next 2 weeks. So as you have received an email from the university saying that we will resume in-person teaching on January 31st. However, I also received another email from the academic senate saying that instructors may opt to teach 2 more weeks of remote teaching just as a way to observe the pandemic trends. So I think I will take that option just for everyone's safety. And also I think probably remote teaching for this class would be as effective as it should be, right? Because people can see the recordings better than if I teach in the classroom. That's what I think. So I will take this option and continue our remote lectures until the end of, the Wednesday of week 6, sorry. That will be February the 9th. So we will see what will happen. And then possibly if we will go back to in-person teaching, the first in-person teaching date will be February the 14th, the Valentine's Day. So we'll see. But in that case, we'll also see whether we will find a better classroom for that. Yeah, so these will all be depending on the situation, because I think for Monday, my original plan for the in-person teaching is that I actually reserve a room in the Boyer Hall, so that will be the seminar room for the 4 p.m. bioinformatics seminar. I think that can save students from walking, right? Otherwise, I think the scheduled classroom is very far away. But now I think the bioinformatics seminar will be remote for the whole quarter. So we'll see. If we go back to in-person, probably we will use that Boyer room as I planned. Okay, so another thing is that the final project data has been posted to the CSLE homepage. If you can check, there is an assignment item there for the final project, and there is a detailed description about the data set and the paper. So the data set will be, I should say multiple data sets are from a recent benchmark paper about single cell multi-omic data integration methods published in Nature Methods. So the nice thing is that the authors have really cleaned up the data and post the process data to a website called Figshare, and then you can download the process data from there. And the data are already in the matrix format and called the HD5 files, and you could process them using the SCAMPy, SCAMPY Py package, a Python package which can directly take those data as input. So yeah, I would suggest that you can check the data out and start playing with them early. And also, we don't require people to use all the data sets because there's a lot of data sets, but I would encourage you to pick a subset of the data sets based on your interest and your computing ability and the question you come up with. So that's the idea for the final project. So please start early, try to find your partner if you want to form a group, and try to look at data early. So don't wait until the last minute. That's my suggestion. Okay, any other questions before we start today's lecture? All right, so if not, so we will continue our lectures from last Wednesday. So give me a second for sharing the screen. All right, so last time we talked about multiple testing, right? After we spent, oops, I think my screen sharing is paused. Let me see what happens here. Okay, so let me see. Okay, you should be able to see it. So after spending several lectures talking about hypothesis testing, and that's about one test. And just as a quick recap, we talked about the t-test, and we said that there could be parameter estimation inaccuracy if the sample size is too small, right? In particular, how to estimate the pooled variance. That could be inaccurate, and the variance of our estimator could be too big. So to address that issue, we talk about the Bayesian idea, try to come up with a Bayesian estimator to have a smaller variance at the cost of adding some bias. And we also use that example to talk about what we mean by empirical Bayes, which we will also see again today. Okay, so following that, we said that in bioinformatics or gene expression data analysis, we are not doing just one single test. Instead, we do multiple tests, one per gene. So the number of genes to check for DE will be equal to the number of tests. So in that case, we would need new criteria to better address our scientific question. The motivation is that if we still use the significance level, which is as the upper bound of the type 1 error we make per test. Type 1 error means that the gene is not DE actually, but we mistakenly call it as DE. And if we control that probability to 5%, it's a conditional probability, conditional on the genes not DE. So if we control that conditional probability to 5%, then as our number of genes increase, then the number of false positive genes will increase accordingly. And that may not be the thing we want. Right? We don't want to have 400 false positive genes in our discovery. So therefore, we need a better criteria, not the significance level. So in this case, the most conservative criterion is the family-wise error rate. That means the probability of having any false positives. However, because we don't want to assume any arbitrary independence about genes, right? That's not realistic. So therefore, the only rigorous upper bound we can set on this family-wise error rate is by this union inequality. So the probability of the union of sets is less or equal than the sum of the probabilities of each set. So with this very loose upper bound, it could be very loose. Actually, we found that to control the family-wise error rate, the significance level must be set to the error rate upper bound, say 5%, divided by the number of genes. And that could be extremely small. And we may not have any p-values under this. So that will lead to no rejection, no discovery, and clearly undesirable to biologists. To address that issue, an alternative criterion was proposed in 1995, and this has become the dominant criterion. It's called a false discovery rate, short as FDR. And its definition is that among the discoveries, the rejections you made, what proportion is false? And this proportion is called false discovery proportion, short as FDP. And the FDR is the expectation of the FDP over all potential samples. Okay, so in other words, this is a frequentist criterion, meaning that we consider each sample to be random from some distribution, and we fix the distribution parameters. We don't consider them to be random. So that's not Bayesian. All right. And last time we stopped at talking about this Benjamini-Hochberg procedure, BH procedure, which relies on accurate p-values. Recall that two lectures ago, we talked about that p-values must be well calibrated by following a uniform 0 to 1 distribution under the null. That's a sanity check of the p-values. And here, this Benjamini-Hochberg procedure assumes that the p-values are already well calibrated. And then let's say we have p genes. So we have p-values. We sort the p-values from the smallest to the largest. And for each p-value, we compare it against an increasing threshold. So the threshold increases with the order. So say if there's a first one, then I is 1, second one, I is 2. So each order p-value has its own threshold. And we basically go to the order until that the p-value exceeds the threshold, and we stop there. And we just go back to the previous one where the p-value is under the threshold. Also, the p-values before this one are under their thresholds, then we reject those. So that's the idea of the Benjamini-Hochberg procedure. So in other words, the illustration is that we order the p-values from the smallest to largest, and we draw this straight line indicating the increasing threshold, and we just find which is the last p-value for which itself and all its previous ones are under the line. And then we find it, and then we reject those hypotheses. So very simple idea. But last time we didn't talk about why this works. So to rigorously prove why this can control the FDR, which seems to be magical since the FDR is an expectation. And as I said, when we calculate the expectation, we need to know the distribution of our data generation. However, we don't have that information here. We are not assuming the data come from any distribution. So therefore, the expectation cannot be computed analytically, right? We cannot calculate it and control it under some alpha or under some 5%. That's not doable. Then how can we control the FDR? Then that's the smart question, right, to ask. And actually, I think the proof in the original paper was very lengthy, but later a simpler proof was proposed using the technique from probability called the martingales. So if that's something you learned before, then you may check it out to see why the FDR is controlled. But for here, we're not going to give you the rigorous proof, but we're just going to give you a sketch to give you some intuition behind why this works. Okay, so this intuition is that, let's put it here. The intuition, you can see it actually makes sense. Proof sketch of this FDR control. So it's about why BH controls the FDR. Okay, that's the foundation of why this algorithm works. So let's say that we conditional on our rejections we have K rejections. Okay, so this means that we have K identified DE genes. An algorithm calls K genes as DE. Okay, and then we just say that we look at this conditional expectation. So before, this is the FDR, right? Expectation of V given R. Recall that V is the number of falsely identified DE genes. So let's do conditioning by letting R to be known. So in this case, what this conditioning will help us is that previously, when we take this expectation, the challenge is that both V and R are random, and they're random variables because our sample is a random sample. So that's why applying the same procedure to a random sample, the number R and the number V could change, could be random. So that's why we cannot easily put expectation around the numerator and denominator separately because we know that's wrong. When we take expectation, we cannot do that. But with this conditioning, now the denominator becomes known. That can simplify the task. So you see, we can just put the expectation around the numerator. Okay, and what's the numerator? Based on the discovery, recall that, let's say the BH procedure finds that we would reject p-values. Say BH rejects p-values from the smallest one up to the kth one. Let's say this is the kth order, okay? Let's call this the kth order. That's where we do the rejection. So therefore, you see, when we do this rejection, this is equivalent to say that the significance level we set for every test is equal to PK. And there's a hand here. Aditya, do you want to ask the question?
Yeah, I wanted to ask, so I get why we pull out the 1 over K, but why can we drop the conditional for V? Like, is it not, like, I guess I'm not understanding why we got rid of the expectation of V given R equals K, or are those like independent or conditionally independent or something like that that allows us to do that?
This is just this holds in general. We're not, so the reason we put this unconditional is just because they are not independent, right? So let's say that based on your question, if V and R are independent, which cannot be the case because V depends on R. But let's just say if they're independent, right? Then based on the rule of independence, what we can write is we can factorize these two things. This is what we can do, right? This is what we can do, but we cannot go beyond here. So the thing is that, but in general, right? In general, this is always wrong. So like we cannot write this expectation of ratio as the ratio of expectation. This is wrong. So that's why we cannot do it. So in order to just put the expectation around the numerator, put a conditional condition on the denominator is the only way to go.
Right. Sorry. So my question was, since we know that V and R are not independent, then doesn't that numerator, like the new numerator expectation of V, like doesn't that also need to be conditioned on R being equal to K? That was the question that I was.
I get a question. Yeah, that's a very good question. Actually, we should do that. I think you made a very good point. Actually, rigorously, we should put it here. That's correct, right? I think, is that your question?
Yeah. That
okay.
that was what I was curious about. Thanks.
Okay, thank you. Yeah, that's great. Yeah, this is right. Okay. And now let's move back to here. So say that the BH procedure finds the p-value cutoff, pk, the kth order p-value, then it's equivalent to say that we are basically setting the significance level of every test here, every of the p tests to pk. That means we compare the p-value to the threshold, to the significance level. If it's less or equal than that, we reject. Otherwise, we don't reject, right? This is exactly corresponding to that. So therefore, what we can say is that, coming back to here, so what's the number of false positives when we set this significance level to pk? Let's answer this question. So recall that we have this result coming back here. So when we talk about the family-wise error rate, we said that, so we are looking at this union of set, right? Whether this gene J is a false positive. And we were saying that this probability is less or equal than the number of genes times the alpha. That's the family-wise error rate. And then for the previous one, let's say the expected number of false positives. So it should be the number of non-D genes times the significance level. So we have seen that. And we know that the number of D genes is less or equal than the number of genes. So based on here, we can set an upper bound as the number of genes times alpha, right? Because that makes sense, because number of D genes non-D genes must be under number of genes. So then moving back here, this is exactly the expected number of false positive. So basically, this will be less or equal than the number of genes, which is P here, okay, times the significance level, which is this pk. Okay, and K is our number of discoveries. Okay, and then divided by K. So we have that. So finally, what we can say is that using the threshold, what is pK? What does pK satisfy? By the threshold, we actually have pK as the last one that is under the threshold. Let's say the threshold is 5%, okay, divided by P times the order, which is K. We have that. So we put this fact into here, and this becomes P divided by K times PK. And I put in what PK is under, so this becomes inequality. PK is under 5% divided by P times K. So you see, we get 5%. So this is just a sketch to show that conditional on a particular number of rejection, we can control this conditional expectation of the FDP under our target FDR 5%. So then you can see we can make this statement more rigorous using the martingale. Okay, so hopefully I think this can give you some intuition about why this makes sense. And the key here is that we are using this changing threshold, okay, and try to link the last p-value to be rejected to the significance level. Okay, so therefore, to summarize, the FDR is what we use as the most dominant criterion to control false discoveries. And related to this FDR, we also have a term called John Story, who is a professor at Princeton. He has a famous paper called Q value, John Story's Q value, which is closely related to FDR with some small modifications. So basically, he invented the idea called positive FDR, which is defined as the expectation of V over R conditional on R being positive. So it's a conditional expectation, but I will say this is a technical change. But anyway, so the Q value application-wise, what the Q value does is that it will try to assign every gene a Q value. So gene I will get a Q value I, and then I from 1 to P genes in total. So the Q value can be considered as an alternative way for controlling the FDR. So just like when we have significance level, which can correspond to P value, right? So there's a FDR, which can correspond to Q value. So the idea is that when you have a significance level preset, what you can do is that you compare every gene's Q p-value to the level. If the p-value is below the level, you reject the gene, call it DE. Similarly, once you have an FDR preset, 5%, you compare the Q value of every gene to the FDR. If the Q value is under the FDR threshold, reject the gene. So the same logic, same idea. Okay, but so I will not spend time to talk about the Q value exact technical definition, but you guys can check it out if you're interested. But I would say it's a slight modification of the P value and maybe slightly more powerful because it modified a little term there to make sure that it's less conservative. But in many applications, the two things are pretty similar, I would say, based on our experience. Okay, so following this, right, multiple testing, we have talked about this so far, and we can also think about something which I consider as some interesting open questions to think about. So let's say, if you recall, I mentioned that I wrote a paper about multiple testing and binary classification, right, in that setting. So following that paper, I want to say that the similarity between multiple testing and binary classification is that we are going to make many, many binary decisions at once. So therefore, regarding that, the decision we make can be summarized into what's called a decision matrix. So let me just make it here clearly. Okay, so the decision matrix. Let's say that we are going to make M decisions in total. Okay, each decision could be a test, could be a classification rule, could be a classification decision. But here the key is that we need to differentiate what's the truth and what's the decision. Okay, to make it simpler, what I want to say is that we just say the decision is binary, 0, 1, and the truth is also binary 0, 1. And we count how many decisions belongs to, and here's the total. And this is the total. So we are interested in among the M decisions to be made, how many are consistent with the truth, right? So the diagonal terms will be nice. So let's say that we denote that for the truth being 0 and the number of 0 decisions we made as S, and for the truth being 1 and the number of 1 decisions we made as U. And we call this as T, this as V, and this as R. And let me see, I think I made a mistake, sorry. I think to be consistent with my notes, I would like to swap it, sorry. So I put 1 first, 0 next. So 1, 0, 1, 0, and this will be R, This is M minus R. Decision. Sorry, I think I also need to swap those two. Decision as the row, truth as the column. Okay, so these are truth. True 1, true 0. Decision 1, decision 0. Yeah, that makes sense. So here, when we reject genes, we reject R genes. That means our decision is 1 for R genes. And our decision is M 0 for M minus R genes. Let's say here M is the number of genes. Okay, and let's say for this means true 0. Let's denote it by M0. And the remaining is M minus M0. So you can see that here, I intentionally use lowercase symbols to mean non-random numbers, like the total number of decisions or genes is non-random. The total number of zeros is non-random, it's the truth. And the total number of ones is non-random. But anything based on our decision, that's based on our data, right? Since data is random, as a result, the decisions are random. So these were denoted by uppercases. So I intentionally did that. And the reason I want to write this table is because I want to introduce some key concepts we see a lot in bioinformatics research. So when we were trying to make so many decisions, right? What are the concepts we can use to evaluate the performance of such a decision matrix? As I said, if all the things, the numbers are concentrated in the diagonal, like S and U are large, T and V are small, then it means that we are doing a good job. Otherwise, we're doing a poor job. So first of all, people are familiar with what we see as the ROC curve. Okay, so in the ROC curve, what are we actually plotting? So what we are plotting is actually, this will go from 0 to 1, and this will go from 0 to 1. And we know that a perfect ROC curve should look like this. Okay, so the area under the curve should be close to 1. That means it's very nice. But what does it mean? So basically, there are several ways to say it. Some people call the y-axis specificity. You will hear that. Some people call this as 1 minus sensitivity, which means that when the sensitivity is, let me see, when the sensitivity is let me see if I'm right. Yep, when the sensitivity is 1, that means we are right here. So it means that we are super sensitive. But in that case, a poor method may have low specificity. That means it can detect a lot. So the curve may be very bad. So the null case, right? The worst ROC curve you can expect is the diagonal line. And you cannot do worse than that. Because if you do, you should just swap your labels and try to reassign your decisions 1 and 0. And you can do that. So that's why this is the random guess, which means that you will have a half chance to make mistakes. Okay, so that's why I'm going to try to define those terms for you. So what is the sensitivity? So sensitivity is basically, it means that if we have the true case as 0, the truth as 0, will you call it as 0? So basically, sensitivity can be regarded as among the true zeros, what is the chance we call it 0? So it's U divided by M0. So M0 is the true number of zeros, among which how many are we calling 0? And specificity, on the other hand, it's actually when the truth is 1, M minus M0, and how many cases are you going to call it as 1? So it's S divided by the number of true ones. Let me see if I made a mistake, actually. I think I need to check it to see if I swapped those two. But for sure, it's one is that, one is the other. Just give me a second. Okay, sensitivity. Yeah, I think I swapped the two. Sorry, my bad. So this should be the sensitivity. Among the true ones, how many are called ones? And specificity is among the true zeros, how many are called zeros? Yeah, that's right. So that's why, based on the definition, we can also have specificity called the true negative rate. Okay, among the negatives, what are the among the true negatives, what are called negatives? And sensitivity as the true positive rate. Okay, so therefore, because I made a mistake before, here the x-axis should be 1 minus the specificity. That should be correct. And the x-axis should be the sensitivity. So I should swap those two. So in other words, you can also say the sensitivity as the 1 minus the false positive rate. So that's why I can also say the x-axis of the ROC is 1 minus false the specificity. Yeah, 1 minus the false negative rate. It's false negative rate, 1 minus the true negative rate. And here is the true positive rate. So these are the things people can use to label their ROC curves. And also related to what we just said, we can have two more things that can be introduced. One is so-called the precision. Precision is that among your discoveries, among the ones you caught, how many of them are true? So therefore, based on what we said, precision should be S over R. So it's dividing by the row sum here, while recall is equal to sensitivity. So sensitivity is also called true positive rate and also called recall. So in other words, when we say precision and recall, so this is also another curve called precision recall curve. You will also see short as PR curve. Okay, so when you have this, then you can have the curve labeled as precision in one axis and recall in another axis. So basically, the curve would look like precision in the y-axis, recall in the x-axis. But here you will no longer have a monotonicity in your curve. So it's possible that as you, definitely you expect that as the recall increases, you're going to find more and more as S, right? So when you increase the recall, you just want to call more things as one, increase the S, and you achieve that. But on the other hand, it doesn't mean that your precision would always decrease or increase. The precision can fluctuate. So it's possible that you will have a precision recall curve like this. That can be possible. So here we still want to compare the area under the curve. The larger, the better. So you can see what's different here is that in the ROC curve, the two denominators are both the truth. It's one of them is M0, one of them is M minus M0. So they are the truth. While in the precision recall curve, for precision, the denominator is the number of rejections, is the random R. So that's the difference. And also the numerator of precision recall curve are both S. So why would some people use precision recall curve instead of ROC curve in their evaluation? The reason is that precision recall curve is less sensitive to class unbalance. So less sensitive to the discrepancy between these two numbers. So for example, if m minus m0 and m0 are very different, this is what we call the unbalanced scenario. So in this case, the ROC is not really that meaningful because you could just predict, make the decision just to cater the major class. So for example, let's say that if, let's say if M0 over M is larger than 90%. Okay, so this M0, the true zero dominates. So in this case, when you make a decision, you could just naively predict every decision to be zero, right? So if you do that, you make every decision to be zero, so your decision will just be in this entry. So basically, given the truth being this and this, your decision will only be in this row. You will only predict zero. So in this case, even though you may have a very bad, so in this case, let me say that you predict just zeros. So then your specific sensitivity here will be U over M0. So since you predicted, let me see. So yeah, so sensitivity is S is 0. So your sensitivity is 0. But in that case, your specificity can be perfect. So what I'm trying to say is that maybe it's not easy to just say it here, but I'm trying to say is that in this case, if you just make that naive prediction, you can have a very perfect ROC curve, but that doesn't mean this result is useful. However, if you have this precision recall curve, since you are going to decide it based on the precision in particular, it's dividing the R. That's the number of rejections you are going to make. Then naively predict everything to be zero will not be good, because basically here the denominator becomes zero and there's no prediction at all. So you will set that in that case, the precision to be zero. So you have zero precision, and that's not good. So that's why when your class is unbalanced, then the PR curve, the precision recall curve, is more informative than the ROC curve. Okay, but I want to say that these concepts I introduced here, the ROC curve, precision recall curve, the sensitivity, specificity, true positive rate, true negative rate, those are all used as concepts in binary classification settings. So in other words, in this binary classification setting, you are making M decisions for M observations, for M data points, and you want to have an overall evaluation of your prediction accuracy using these things. So even though these are concepts in the classification setting, but one interesting thing we can see here is from this precision definition. The precision definition can be seen as defined as 1 over V divided by R, right, based on what we said. So, and V divided by R, we know in our multiple testing context is called false discovery proportion. So in other words, if you think about it, then the FDR is like, so this is like 1 minus FDP. And then FDR can be think about as the 1 minus expectation of precision. So if we try to link the two framework, we can see this connection. However, what's different here is that when we talk about binary classification using the ROC curve or precision recall curve, we are never thinking about expectation. In other words, these are just the numbers we observed from our data. We're not talking about expectation at all. While in the multiple testing scenario, the criterion we use, FDR, is an expectation. It's not just about the particular sample or the particular decision we make. It's about every potential sample we could observe, and on average, what would it be? So this is another case where you can see the distinction between the prediction perspective and the statistical inference perspective, which we said in the first class. So when we talk about inference, we always want to see beyond our sample. So that's why we talk about expectation, which is a property about the population, the potential samples. While when we do this prediction problem, as in binary classification, these numbers would just calculate it based on what we observe, the particular testing sample or validation sample we have. So we compute those numbers and we use those numbers to make the curve. So I don't know if I make this clear or it's more confusing to you. So if you have any questions, you can let me know at this point. So the key is that for binary classification, at least when we calculate the ROC curve and the precision recall curve, we don't think, there's no thinking about the population involved. We're just using our validation or testing cohort as a representative sample to do the calculation. Okay, so maybe a take-home message for this part, I know I said a lot, probably not very clearly, is that if you are going to use ROC and precision recall curves, right, in your research, that's the case where you are doing binary classification. Let's put it that way. So you're trying to make a decision for a particular observation, and that's not based on a test. That's based on a classification algorithm. Then you will use ROC and precision recall. On the other hand, if you are doing that multiple testing framework, in other words, for each feature, like every gene, you're going to test some hypothesis, you'll use a p-value, and then in that case, that's multiple testing, then the FDR is our criterion. But the similarity is that both the FDR and those precision, recall, sensitivity, specificity is a collective criterion. We're looking at our M decisions, whether from classification or from testing jointly. So this is about the global behavior, not about a particular decision. Okay, so any questions before we move on to the next topic? Okay, so I think this is quite enough for what I want to say in this class. But just for some of our students who are familiar with binary classification, those algorithms, I want to say a little more about my research, something I've done before, which is that, as I said, when we talk about this ROC curve, it's only based on a particular test sample. So we didn't talk about population, that's what I said, right? But if we want to go beyond that, let's say, given my classification algorithm and the threshold, right, I can make decisions. How would I know this decision, my algorithm would perform like on the population? So let's say, what will happen to the sensitivity and specificity at the population level beyond my current testing sample? So to answer that question, we actually had a previous line of research, which we called the Neyman-Pearson classification, which borrowed the name from hypothesis testing, because in hypothesis testing, a very important theoretical result is called Neyman-Pearson lemma. And that one tells us that if you want to have a powerful test, given a significance level, then the most powerful test should be designed based on the likelihood ratio test. So that's something that's frequently used in statistics when people can write down the likelihood under the null, under the alternative, they could do the likelihood ratio test, and that's guaranteed to be powerful by the Neyman-Pearson lemma. While borrowing that term, in our Neyman-Pearson classification, what we try to say is that we want to control the classification type 1 error, which is 1 minus this true negative rate. So false positive rate. So it will be actually this V minus M0. Okay, so we want to control that V over M0 under some preset bound, say 5% with high probability. So when we say with high probability, we are thinking about population. We're not just thinking about this particular testing sample. So I just want to let people see that there are a lot of things we can say beyond our sample, even though in bioinformatics research, many people are just plotting this ROC curve and the precision recall curve to justify, oh, my algorithm is better than their algorithm, the existing algorithms. But we should bear in mind that this particular curve here is just a realization. And in this class, I want to make people aware that we need to consider uncertainty involved, right? How uncertain is your curve, right? Should we give it a confidence band in some way? And the Neyman Pearson classification actually offers that. So basically it says that if you really want to control one type of error, it could be the false positive rate, could be the false negative rate, you treat it very seriously. You want to make sure that your algorithm performs well, not just on your data, but on more and more data with very good performance guaranteed. Then in that case, we should design our algorithm in a quite different way. Basically, we need to set a threshold of our algorithm in a quite different way. So that's the take-home message I want to say. So this FDR is about controlling the expectation, which is also saying that, oh, I'm not just worrying about this particular data. I want this multiple testing threshold to do well on average on potential samples. That's what we want to have. So expectation is one perspective, while high probability control is another perspective. So probably I'm going a little bit too far here, but I just want to say that in statistics, we care about uncertainty, and we can have different aspects to talk about how an algorithm performs in general, not just on this particular sample. And on average, expectation is one perspective, and high probability upper bound is another perspective. Okay, so that's enough. I'm going to stop here. And so after the multiple testing, right, when I said that we want to make sure, actually, before we do any gene differential expression analysis, I said one particular thing we need to think about is whether our data are really comparable. By comparable, I mean that, say, if you recall for gene I, okay, a one gene. Let's say that if you recall, we have the setting as this gene I has m measurements under one condition and n measurements under another condition, right? That's our setting. But a thing I didn't touch yet, which is very important in practice, is whether these values are on the same standard, on the same ground, are really comparable. That's the question. M plus n values right? If they're measured in different ways, for example, like when I do the measurements for condition 2, my machine had some issue. So all the values suddenly become larger than they should be. Then in this case, doing differential analysis will become meaningless because the values in condition 2 are expected to be larger than condition 1. And that's not what we are interested in scientifically. Okay, so if that's the case, to answer this question, we have many names for it. So it could be called data normalization. It could be called batch effect removal. So these things are actually talking about the same thing. So the key is to make your data on the same ground so you can compare the numbers. So I will use sequencing data, which are count data, as the starting point or as the background for this discussion. The reason is that now in bioinformatics research, genomics research, the standard is to use gene expression count data, right? Nobody are using, I wouldn't say nobody, that's too extreme, but few people are still using microarray as the measurement, but still have some public data to use, so that they can still be valuable. But for the new data generated, they are often next generation sequencing data. So let's say that in the stage of bulk RNA-seq data, RNA So in that case, then we actually have M and N biological samples that are sequenced separately, okay? Separately. That means I do N sequencing experiments and I do N sequencing experiments, just like I do replicates, right? For each condition, I do 3 replicates each. So M and N equals to 3. So in that case, one factor people should definitely consider is total sequencing depth or library size. So they may have different sequencing depth. So what does that mean? So let's say that I'm now going to make the case as, say, I will consider all genes together. So let's say that, let me see, what notation do I want to use? Maybe I'll stick with that. So let's say that I call this gene I's first measurement to gene I's nth measurement. Okay, I just add I as a first subscript to my counts. Okay, so that I can talk about sample J. So let's say that for sample J, I list all the counts I have as X1J to XPJ. Okay, so because I have P genes measured in total. So then sample J's library size can be defined as, let me just call it SJ. It can be defined as the summation of I from 1 to P, Xij. In other words, I take the sum across my P genes. Okay, and let's say that I want to compare different samples. Let's say that I have another sample, J prime. So the thing is that if Sj and Sj prime are not equal, it could mean that I sequence the 2 samples J and J prime at different sequencing depth. By sequencing depth, I mean how many number of reads I get from each sample. So if their numbers are too different, then I may doubt that for my particular gene I, Xij and Xij prime. So for gene I, its counts in the 2 samples may not be comparable. This is the whole question of doing normalization. So what's the intuitive answer for doing this, right? I would say if you just encounter this problem as the first users of RNA-seq data, I think the most intuitive answer is to normalize the count by the total sequencing depth to make the total sequencing depth equal. And that's actually what people are doing. So to normalize by total sequencing depth is still quite common. So let me say this. This is the first approach, normalize by total sequencing depth. But then I will leave this question for you to wonder, is there any issue with this approach? So to do this, what we can actually do is to calculate a weight factor for every sample J. Weight, we call this WJ, okay? So this WJ is defined as whether I should increase my sample J's count or decrease my sample J's count so its total sequencing depth is matched with other samples. So the most straightforward way is to define this weight as the average of all samples total sequencing depth. So now for this case, right, I try to simplify my problem a little bit. I will just assume that I have J sample, I have N samples, I put it here. So without worrying about the conditions here, let's forget about condition first. Let's think about we have N samples that should be comparable. So in this case, what I would actually do is that I would define this WJ by the average. Okay, I'll just call this J prime as a new index. J prime goes from 1 to N. I take their average and I divide this average by Sj. So you see, this intuition is that if Sj is larger than the average, then Wj will be less than 1. So I will shrink the sample just count. Otherwise, if Sj is smaller than the average, I need to increase it, and then the Wj will be larger than 1, and that's what we want. So then you would define, so then the new count for each gene, let's say I call that Xij star for gene I in sample J, just as the original count Xij times Wj. So very straightforward idea. Try to do recalibration to make sure, and you can easily verify that with the new counts, then their sum of all the genes in every sample J will now become equal for different samples. That will be straightforward. Okay, then the question I have for you is that, do you think this makes sense, or do you see any problems with this approach just to normalize by total sequencing depth? An open question I have for you guys. Or maybe the question can be formulated as, under what scenarios is this approach reasonable? Under what scenarios it is not?
Well, it's reasonable if you have like, if each gene produces the same amount, roughly produces the same amount of fragments.
Yeah.
But because genes are different lengths, you'll simply get more fragments, even though your actual expression might be the same.
Yeah. That's a very good point. So this only makes sense that when you do expect the genes, or in total, all the genes together should have the total amount of RNA molecules in each sample. If you do expect that, then this makes sense. Otherwise, it could be that in one sample J, all the genes are more highly expressed. For example, the sample J could be from like an early embryonic stage where all the genes are undergoing rapid expression. So there are a lot of RNAs there. And while another sample can be a later stage where it's more silent, the genes are not expressed as much. So in those two cases, if you assume the total number of reads, the sequencing depths are equal, then you may mislead people. So that's the problem here. So the assumption, we should make it very clear, is that all samples have the same amount of transcription. Right, so total transcription, I think that's the key to justify this normalization. But as I can tell you that no normalization or batch effect method will work universally because they each have their own assumption. And the key is to really think, does this assumption make sense for my data? If the samples are not expected to have the same amount of transcription, then normalizing them to have the same equal amount of total transcription could be problematic. But I want to step back a little bit to say that even though it's problematic, you still can use this to interpret your data. Just to say that here, what I'm looking at is the relative transcription, not the total transcription. Okay, but if this assumption doesn't hold, you can still do it, but you need to interpret the new count differently. Interpret this Xij star just as the proportion of gene I among all genes in sample J. So now you cannot consider this new count as an absolute transcription level. It can only be interpreted as a relative transcription level among all genes. If you interpret that way, then you can do it. But then when you do the DE analysis, okay, coming back here, if you are interpreting this as the relative expression level, then coming back to the DE, then you're saying, does my gene I have different relative expression level between the two conditions? So then the scientific question is changed. It's not like the absolute expression of this gene I, but the relative expression of gene I within the transcriptome. Does that make sense to people? Okay, thank you. All right, so that's the first thing I want to say. Okay, but if you have some additional knowledge, let's say that if you know some genes have very constant transcription levels across samples, you can do that. Normalize by a subset of housekeeping genes. This is the second idea. So here the idea is that if you know some genes that are constantly expressed and you expect their expression levels to be not changing too much, then you can just calculate this factor just based on the sum of the subset genes expression by the sum of this subset genes expression levels. So you don't use the sequencing depth, that's the sum of all genes. Instead, you do this partial sum just based on the subset of genes to do the normalization. But I would say that this will depend on how you define housekeeping genes, knowledge, or you may have some external information. But anyway, this could be available for some systems that people understand quite well, but may not be that universally good. Because even if you check the literature, you can see there are debates about whether housekeeping genes should be interpreted as constantly expressed, or they are always expressed, but can we assume that their expression levels never change? I think there's some controversy about that. So therefore, I would say this is an interesting idea, but we should also be aware that adding this choice of a subset can add some additional arbitrariness into a normalization. So that's something I want to say. But still, it's something we can think about. And I would say for experimental biologists, this is a lot of things. They use this constantly. Like when they run the Western blot for measuring protein expression, they will add some standard. And that standard is something they know, okay, whose expression doesn't change that much. Okay, that's the second thing. And the third thing I want to say is a very interesting idea that I want to introduce. It's called the quantile normalization. Okay, and also all the discussion we have so far is about the bulk RNA-seq data, and we'll go to single cell data later. So for quantile normalization, the idea is very straightforward. So what we want to say is that for each sample J, we can obtain a distribution of all genes expression levels in the sample J. So we have a distribution defined by, or statistically, I should say more exactly as the empirical distribution. So by empirical distribution, I mean the distribution defined by a set of numbers. And here the distribution is defined by those genes, X1J to XPJ. So these P numbers will give me an empirical distribution. And so I call this, let me denote this by fj hat for the empirical distribution. And then you can see that for my n samples, so I have f1 hat to fn hat, right? Each sample has an empirical distribution for the n sample, n biological samples. Okay, I have those. And then the quantile normalization is just trying to do some adjustment to make those n empirical distributions exactly the same. Okay, adjust f1 hat to fn hat to be exactly the same. That's the goal. And how do they do it? Actually, the idea is very interesting. So let me just talk about this in a high level. So on a high level, what they did is that they try to sort, basically, okay, so they try to match the quantiles of these n distribution. So by quantiles, I mean, okay, so here we have the quantiles. So by quantile, I mean here in this, say fj, okay? So fj hat, its quantile would be, I sort those values from the smallest to the largest. Sort x1j to xpj. After sorting, I just denote them as, say, x parenthesis 1j for the smallest, less or equal than x parenthesis pj. Okay, after the sorting, then I will call this as the 1 over pth quantile. Okay, and I call this as the p over pth quantile. That's it. So it corresponds to their order. So, and it's this quantile definition is based on the cumulative distribution functions inverse. That's how we define it. Okay, so thinking about this as the quantile like this, then what I would do is that I would define a new distribution called f hat by averaging the quantiles of all the n distributions I obtain. So say here, this one would have its 1 over pth quantile equal to the average of those. So I would do 1 over n, the average. Okay, so j from 1 to n, yep, x1j. That's what we'll do. So in other words, I took the minimum of each sample. I took the minimum of each sample and compute the average of the minimum. And similarly, for the maximum quantile, so I skipped the middle ones, but for the maximum, the p over pth quantile will be the average of the maximum of every sample, p. Yeah, so that's how I define it. Okay, so now you see this f hat will also have p values, p quantile values from 1 over pth quantile to p over pth quantile. Then finally, I'm going to use this f hat to replace all the f1 hat to fn hat. So in other words, what it means is that, so finally, what I would do is that, say for sample j again. So let's say for xij, okay, I want to know what's its order in the sample j. Say its order k, it's ranked as the kth smallest one. Then I would replace it by the k over pth quantile of this f hat. So I will just pick that corresponding k over pth quantile from f hat, use it to replace xij. That's the whole idea. So in other words, after this quantile normalization, all my n samples, for each n sample, I have p numbers, okay? And these p numbers will be the p quantiles of this f hat. So after that, every sample j is just a new permutation, new ordering of the p values of the p quantile values of f hat. Okay, this is the high level introduction, and I will give you a concrete example to wrap up. Okay, so let's go to this concrete example. Let's say that I will try to simplify this a little bit, make it even simpler than my notes. So let's say that I have just 3 genes. Gene 1, 2, and 3. And let's say that I have 3 samples. Sample 1 and 2 and 3. Okay, let's say my gene 1 has 100 in sample 1, 80, sample 2, 60, sample 3. Gene 2, 50, 90, 50. Gene 3, 30, 20, 30. Okay, so with this case, then sample 1 has an empirical distribution at those 3 values with probabilities 1/3 each, and sample 2 has an empirical distribution 3 values also, sample 3 3 values. So you can see that they definitely have 3 different distributions, and now I'm going to match it. Okay, so firstly, let me sort the let me see. So let's see that we first get the rank. Okay, so sort within each table, within each column. So sort each column. Okay, then this will give me rank 1, 2, 3 instead of gene. I'm only looking at the ranks. And sample 1, 2, 3. So then for sample 1, the smallest is 30, second 50, 100. So this is just to get the 3 quantiles of my sample 1's distribution, right? Minimum, middle one, largest. This is 20, 80, 90. This is 30, 50, 60. Okay, so with this, now I'm going to get that combined distribution by taking the row averages. Average each row. So then I would just have rank 1, 2, 3. And this will be the averaged distribution. So this will give me, see, just do a simple calculation, 80 over 3. This is 180 over 3, 60. Lastly, it's 250 over 3. So I get those 3 numbers. So finally, what I will do is that I will put those 3 combined distributions quantiles into my data. So to do that, I would obtain what's the original rank of each gene. Okay, so here I will still have the gene sample, but now I'm going to change the count values to the rank. Just give me a second. So gene sample 1, 2, 3, and 1, 2, 3. Okay, so basically 30 is ranked 1. So I put 1 here, 52, 103. So these are the ranks of the 3 genes in column 1. And here, second column, 20 has rank 1, 80 has rank 2, and the second gene has rank 3. Finally, I have rank 1, 2, 3. So with this, and with the average values of my quantiles of the rank, I get my final matrix. So I put it here, gene sample 1, 2, 3, and 1, 2, 3 here. So basically, gene 3 in sample 1 has rank 1. So I will put 80 over 3 as its new value. Gene 2 has rank 2 in sample 1. I will put the value 60 here. And finally, for rank 3, I put 250 over 3. That's my new value. And similarly, I will do that for column 2. Gene 3 will get rank 1, 80 over 3. Gene 1, gene, I think I made a mistake. Sorry. No, forget about this. So sorry, what I want to say is that, so maybe I should start here. So for gene 1, 2, 3, and sample 1 and 2 and 3. So whenever this is value 1 here, I put the rank 1 value here correspondingly. So it's 80 over 3, 80 over 3, 80 over 3. Whenever it's 2, I put a value of rank 2 here. So that's 60, 60, 60. And finally, whenever it's 3, I put a value of 3 here. So that's 250 over 3, 250 over 3, 250 over 3. So as I said, after this quantile normalization, every sample will have the same 3 values. It's just ordered in different ways, depending on the original rank of the genes in that sample. So why does this make sense, right? You may wonder this. And this has been a quite popular method since it was developed in 2003. I think the main reason is that here the assumption, let me put it here, is that you believe all genes have the same distribution in different samples. Why is this reasonable? I think the biological reason behind this assumption is that even though you think some genes may have altered expression from sample to sample, that's what we call differential expression. However, the majority of genes should have their expression quite stable. So therefore, together, you believe that the majority of genes which will determine the distribution will not change from sample to sample. So that's the fundamental assumption about this quantile normalization. I think I will stop here because we're a little out of time, but I will leave this question for you to think about, right? The 3 normalization methods we mentioned today, do they make sense to you? What are the relative drawbacks you can see from it? And so we will come back to revisit this next time. And also, I think next time I plan to talk about a popular method called countback for batch effect removal, which is based on regression models, generalized linear models. So that's why I will also spend some time to talk about that next time. All right, so I'll see you on Wednesday. And we have a chat box. Thank you.